Okay, so back at the beginning of the semester, we learned how to graph using specific points for individual parent graphs, and then we took the transformations and we applied them to those points in a chart, right? And then the last column of the chart is what we graphed. So we're going to do the same sort of thing here. The reason that I'm having you guys do this is because what I've noticed is that for students who only graph using a calculator for this unit, they tend to forget that there are asymptotes for these graphs, and they get answers wrong that they shouldn't be getting wrong. So if I force you guys to do things by hand, then you will do a better job when you graph it using a calculator on the NCFE. All right, so we have two types of graphs we're looking at. We've got exponential graphs, and those would be in the form y equals b to the x. And then we have log graphs, and those would be y equals log base b of x. So before we even start graphing an exponential or a logarithmic graph by hand, we have to know what the base is because that's going to be important. So if you're graphing something that's exponential, if you think about what would happen if you plug 0 in for x, you would get b to the 0 power, and anything to the 0 power equals 1. So that's going to be the first point you're going to use. Second, you'll think about what happens if you plug in 1. So a base to an exponent of 1 is going to give you whatever the base was. So 5 to the first is going to give you 5. 2 to the first is going to give you 2. 1/3 to the first is going to give you 1/3. So the next point is 1 comma b, and that b is going to be whatever the base is. And then third, for exponential graphs, we have a horizontal asymptote at y equals 0. And that horizontal asymptote can shift up or down. So whatever the shift is, if it goes up 7, if it goes down 2, whatever that shift is, that's going to be what your asymptote is, okay? Logarithmic graphs are the inverses of exponential graphs, and so that means that for logarithmic graphs, we're just going to flip the x and the y for all of these. So instead of 0, 1, we have 1, 0. Instead of 1b, we have b1. And instead of a horizontal asymptote, y equals 0, we're going to have a vertical asymptote, x equals 0. So horizontal asymptotes, those can only be shifted up and down. So whatever your vertical shift is, that's going to tell you your horizontal asymptote. Vertical asymptotes can only be shifted left and right. So whatever your left and right shift is, that's what your vertical asymptote is going to be. Okay? So if we look at number 1, the base is always the thing that has the exponent attached to it. So if you look at number 1, you can see a 2 and an e. The 2 technically has an exponent of 1, which means it is not considered the base for this problem. The base for this problem is the e, because the e has an exponent of x minus 4. Okay? So e is Euler's number. It's spelled E-U-L-E-R. It's named after an old European dude. E on your calculator is right here above the ln, see the blue, e to the x, and so whenever we type in an e, that's how we type it, okay? It's right there. So you'll do second ln anytime you want to type an e in. Okay, so if we start the chart for this graph, we're going to have 0, 1, 1 comma e, and then y equals 0. And what are the transformations that happen on number 1? You got that 2 in the front. Mm-hmm. Do you remember what this does to the point? Makes it different, yeah. Anyone remember what that number in the front is? Vertical stretch. So it's a vertical stretch of 2. Does that happen to the x coordinate or the y coordinate? vertical stretch of 2 happens to the y, right, because vertical is up and down. So we're going to take the y coordinate and multiply it by 2. And I'm literally just going to write 2e because in my calculator I can figure out that decimal in a little bit. Having a horizontal asymptote, the vertical stretch will not affect it. So my horizontal asymptote is still 0. What about this little x minus 4 right here? Right, 4. So the exponent is considered to be the inside of the function. You could put parentheses around the x minus 4, but you don't really need to because they're already kind of up there. So that means we're going to go to the right 4. So I've got 4, 5, okay? And then what's the plus 3 on the end mean? Up 3. So 2 plus 3 is 5, and then we have 2e plus 3, and the horizontal asymptote is 3. So what you're going to notice is that the number on the end is always what your horizontal asymptote is. Every single time. So if there's no number on the end, then you would have a horizontal asymptote of 0. Okay, so let's go ahead and graph this. We have horizontal asymptote of 3. And we have the point 4, 5. And then I'm going to use my calculator to figure out what 2e plus 3 is. So when you use the e on your calculator, 2 and then second ln, it always asks you for an exponent because e typically has an exponent. If you're doing something like this where you don't really have an exponent for it, it means you have a 1. So anytime you go to the default exponent, that's always a 1. So 2e plus 3 is 8.4. So that's the point 5. 8.4 is going to be a little bit off the graph. And then here we have to think about how these graphs work. So you know that your 2 points are going to be connected. We know that that's going to happen. And now we just have to think about what would make sense for an asymptote. We know that when we have a curve with an asymptote, that the curve follows the asymptote. It makes more sense for the curve to go this way than it would for the curve to go back and go this way, because then it would no longer be a function, and that would be weird, okay? So we're going to connect these dots and then follow the asymptote. All right, and if you want to use a calculator to check your answer and make sure it's good, so I just did 2, and then I did my second ln, got my exponent in there. And then there's what my graph looks like, and I can see that it matches what I drew. Okay, let's go ahead and try number 2. So number 2 is a log graph, so we're going to start over here. We have the point 1, 0. What's the base? 3. Log base 3, so 3, 1, and then a vertical asymptote for this one. All right, and be careful when you try to figure out what this transformation is. I'd say about half of you would probably get it wrong. So think about where the parentheses are and why they didn't have to be written. So what transformation is that minus 8? It's down 8. So the reason that it is down 8 and not right 8 is because there's no parentheses here. You can't just put parentheses wherever you want them to be. So if it had meant right 8, you truly would have had to have those parentheses there. The reason they did not write the parentheses is because they would have been right here around the x, and you don't need to write parentheses around one thing. It's silly because parentheses are grouping symbols, and one thing is obviously a group on its own. Okay, so if you had parentheses in this problem, that's where they would be. That means that this is a down 8. Okay, so we'll say this is 1, -8. This is 3, -7. And the vertical asymptote is just x equals 0. And you can't see it very well for this one, but the vertical asymptote always comes from inside right here. And this should take you back to the very beginning of this school year when, well, not the school year, but this semester when we learned about limited domains. One of the things we said about log functions was that whatever you take the log of has to be greater than 0. No zeros, no negatives. And so the inside of the log is what tells you where your asymptote is. So this asymptote, vertical asymptote, is at 0. This vertical asymptote here would be at -5. Does that make sense? So I'm getting that from the inside. All right. So we'll go ahead and graph that. We have vertical asymptote at 0. Point 1, -8. And 3, -7. And then the same thing, we know that the points are going to connect and we have to think about which way it makes sense for the curve to follow the asymptote. It doesn't really make sense to go backwards. There would be like a sharp corner there, so what we're going to do is we're going to have it follow like this. So this next part, I want every single person to have their calculator out because people do have a hard time graphing these. So first, we're going to see if your calculator has the same operating system. So if you're using a school calculator, these are definitely okay. But those of you who have your own calculator, we just want to make sure it's updated. So to check it, you're going to hit the math button right here. And then if you go up, you should see log base. If your calculator has an old operating system, it will not have that. Is everyone able to get to it? Log base. Okay. So base of 3, the x is the only thing in the parentheses, and then -8 on the end. And you guys can see that it matches the graph that we drew. All right. I want you to take a moment and discuss in your groups if you think this graph has a X-intercept or not. All right, so take a moment, discuss. All right, what do we think? Is there an X-intercept? Yes? No? We're afraid to say. So when you look right here, what is this arrow telling me? It keeps going to the right. It keeps going up as well, right? So this graph has to have an X-intercept because there is not an asymptote that keeps it from going higher. Okay, this graph will go up forever. It just goes up very slowly, okay? So if you needed to find the X-intercept on this graph, you could do it, but you have to adjust your window to have a bigger X max. So that's going to make your graph go to the right a little bit more. What do you guys think is a good X max for us to try? Right now it's at 10. What should we try? 30. All right, X max is 30. That did not get us to our X-intercept. Okay, let's try 900. -10 to 900. You don't have an X in there. All right, we didn't get it, so what should we do?
10,000.
Try something bigger, 10,000. All right, so it crossed. You can't see it above, but it looks like it crossed somewhere around here. So I'm going to say second trace, and then which one do I use for an X-intercept? Not intersect. Do you guys, what does intersect work for? You have to have two different lines. I only have one. You have to have two different lines to intersect. So I'm going to use option number 2. I'm going to find the 0 of the graph. I'm going to tell my graph to look at it from 0 to 10,000, because that's how big my window is, and I can't see what it is. The x-intercept is 6,561. So it's there, it's just very large. It takes a long time to get there. Okay, so the reason that I have you guys graphing these by hand is because a lot of students would look at this, they'd look at their original graph, and they would tell me that not only does this have a vertical asymptote, they would tell me it has a horizontal asymptote, and that's wrong. They do not have horizontal asymptotes, they only have vertical asymptotes. Okay, the other thing I want to show you is that these graphs, even though I know it has a vertical asymptote, on my calculator they look like they stop. So most students, if they are only using a calculator to graph these, they will tell me that the graph stops, but it doesn't. It goes down forever. Your calculator has a hard time showing that. Okay? So the reason I'm making you guys do these by hand is because you have to be smarter than the calculator. Okay? All right, go ahead and work on those.